I know a few folks who can't make it for weather or travel, so welcome to the show, those of you who are listening from away. Everybody is finally finished with homework 3, so we can go over that if you would like. So for the most part, the computational things went well. If you're still having any trouble fighting with SAS or SATA to make it do things that you need it to do, please let me help you. I'm happy to do that. But as several of you discovered, getting SAS or STATA to spit out the numbers and knowing what those numbers then tell you are two separate skills. And being able to generate text that describes what the numbers are telling you is yet a third skill that I'm hopefully trying to lead you into by these sorts of exercises
so
here.
Quick question.
Yeah.
After this course ends, will we have access to this this stuff?
Good question. Historically, I haven't taught the same course back to back, and so I leave it up, but I haven't decided what I'm going to do. Because I'm tempted to take it down at the end of the semester because I'll be doing it in the spring, and I don't want there to be two versions that confuse people. So what I would recommend doing is before the end of the semester, log in and save these pages as PDFs. That way you have them. You won't be able to save it as an HTML page. I don't think it will render properly, but you should, yeah, I would try and archive all this stuff just in case. So yes, but yeah, the idea is that these hopefully can provide a template for you to follow in the future, albeit these are more words than I would typically use in a results section because there's extra things here that I'm going over that are sort of definitional. But so just the things here that were tripping people up, variance versus standard deviation versus standard error. That was one that was a common source of confusion. So I think most people got that when you have an empty model, the intercept is the sample mean. In any of the other models, the intercept is the expected outcome when the predictor is 0. So for instance, if we're predicting fits thrown, then the intercept, when you include pleases heard, is that what that means? If you're including age group as a predictor of fits thrown, then the intercept shifts to this. So variance is the squared metric. Standard deviation and standard error are regular metrics, the unsquared metrics. So variance, the estimated residual variance from the empty model right here, for example, that's all the variance in your outcome, and that's in squared. So it's the squared average deviation from the mean for each child. From here on out, if I'm asking for standard errors for the intercept or standard errors from the slope, it's going to be in the unsquared metric. So remember, standard deviation is the square root of variance. Standard error squared is referred to as the sampling variance of the slope. That's not something that you'll typically see, but there is an analog to that. But let's see here. We have the slope standard error indicates the average distance of the sample slope from the population slope. So it's supposed to tell you about the level of replicability, so to speak. You can think of it that way. Lastly, every time you have a significant predictor in your model, the slope is significant. If it's the only predictor that is in your model, that automatically means that the decrease in the residual variance is significant. There is a one-to-one correspondence. The t for the slope, t squared is f for the r square. So it's the slope that does the reduction in variance in each case. In terms of the age group model, the variable was already coded so that 0 indicated 3 years and 1 indicated 4 years. So you did not have to transform it. However, you did have to figure out that because 0 indicated 3 years, the fixed intercept for the model directly gives you the predicted outcome for the 3-year-olds. You have to find what it is for the 4-year-olds as a linear combination of the slope and the intercept. And so that was the, I guess, the only tricky part on that. So any questions on things you missed or otherwise were unclear? And if there's ever a situation where you interpreted what I asked differently than what it turns out I meant, let me know so that I can clarify that wording for the future too. I'm trying not to be tricky in any way. Okay, so you're good on this? All right, homework 4. How's that going?
Oh.
It's not good yet? All right. So I wanted to spend some time going over the coding of the variables again, because that's something that's tricky, particularly the piecewise stuff. And I was debating the merits of showing you alternative versions to try and generalize the concept versus just talking like what the ones that you need to make sure that we don't get confused. Does anyone have a preference on those two things?
Just tell us what we need.
Tell us what you need. Because sometimes when you see it multiple times, like the logic makes more sense rather than just like the one time it seems arbitrary. So I can help you with that, though. So I have it set up here. We can go over the piecewise example again in of education as part of example 5, and then I can show you how that generalizes to your homework. So this is example 5. Based on this picture of the mean for income at each level of education, each year is an integer, it looked to me like there was basically no slope until 11 years, a bump that comes from graduating high school, and then some sort of increase after that. So how do I get these things in the model to be able to test those ideas? So I'm going to pull up Excel here. So I set up a little thing in numbers for us to fill in so you can understand the logic of how the code accomplishes that goal that we have here. So this is sort of the end result that we want to work to.
So this is what dummy coding is
This is not dummy coding. This is coding slope predictor variables.
for piecewise.
Yes. We can do dummy coding if you want.
Sure.
Okay, do you want to start with that instead, or do you want to start with
I
slopes?
don't know if anyone else needs it.
Okay, well, we'll do slopes first, and then we'll return to dummy coding, because the other example we haven't done yet is another version of dummy coding that gives you a different result. So we're trying to unpack the logic by which these statements give us what we need. So first question, where's your intercept going to be? So I know for this example that I'm going to create 3 new variables, because what I want to be able to represent is the change up to 11, the change from 11 to 12, and the change from 12 up to 20. That's what I'm trying to get. So I want the intercept in this case. I decided to put it at grade 11. What that means is that that is where all of the predictors zero out, so that the model gives you the predicted outcome at that grade specifically. Now, relative to that, I have to say how much time, I'm used to time, sorry, that's my other class, how many values different it is relative to that anchor point, keeping the sign of the values. So for instance, if I go here, 12th grade is 1 more than 11th grade. 12th grade is 1 more than 11th grade. To get to what it would be for 13th grade, if that's a thing, what comes next? 2. Yes. 3. Actually, I need to do this here. This one, it's going to be minus 12. This one, hang on. Hang on, let me make sure that this is right. So we have, all right. So we're keeping, in the example, I think I may have actually screwed this up now that I'm doing this in front of you. Isn't that amazing how that happens? Minus 12. So that's what it would be. So we're picking up, this part here picks up the shift, and then this part carries the extra shift that comes past 12. That means that this part has to be shut off where it left off. This part has to be shut off where it left off. These parts aren't active yet. Shut off means like it's not changing anymore. So now we need a slope that captures this part relative to 0. So what is before 0? Negative 1. Mm-hmm. So that's what it's doing. The idea is that it tracks this part as this slope. The jump here is where it changes, and then this part is after 12. And this extra one here is why I'm thinking I may have actually screwed this up. But it needs to be, no, and this is right, this is right. This is why it gets tricky to figure it out. because it's tracking where it changes. It's changing after that. Now your homework. Here is experience, right? And we need one slope that goes from 1 to 4 and another slope that goes from 4 to 7. So let's say that I wanted to do the same thing where I put the intercept in the middle. Like at this point where it shifts is called the knot, by the way. If I wanted the intercept to be at 4, then it would look like that. So this variable then would track the change going up to 4, whereas the second variable would track the change going from 4 as a reference point. So we'll do this one first. After 4, we go 1, 2, 3. Before 4, we go backwards. -1, -2, -3. Now to make sure that the first slope captures only this part and the second slope captures only this part, it needs to be shut off in terms of its values. So prior to this slope turning on to capture the difference from 4 to 7, it would need to be 0. Likewise, to make the first slope shut off after 4, this would need to be 0. With me? Now what you guys are going to do is a variation of this. Let me make another one here, where I asked you to put the intercept at the beginning. Okay, that means right away 0, 0. So I want the first variable to capture 1 to 4. So this one needs to climb. I want the second variable to capture the change after 4. So it needs to start at 4, a 0, and then pick up that way. That means this one needs to be shut off before. And what do I do to shut off the first slope after 4? See, 0 would make it change again. It needs to shut off where it left off.
Keep going.
It needs to be, it doesn't keep going, it needs to be 3. Yeah. So then what you have when you put them together is the change from 1 to 4 tracked by this variable and the change from 4 to 7 tracked by that variable. So then if I did the corresponding SAS code, for instance, if experience, I'm just going to abbreviate here, is, let's go less than or less than 4. We'll say that. Make this, 1 second. If experience is less than 4, then experience 1 to 4 equals experience minus 1. So if the original variable is less than 4, then experience is, the first slope is experience minus 1, because that would get us these 3 right here. If, stop that, experience is greater than or equal to 4, then, 1 second. If experience is greater than or equal to 4, then experience 4 to 7 equals 3. Excuse me. No, hang on, which one am I on? If experience is greater than 4, yeah, then experience 1 to 4, excuse me, we're still on the same one, started going ahead of myself, equals 3. There. So what I've done so far is set up the first line. If experience is less than 4, it's the original variable minus 1. If it's greater than or equal to 4, it's the original variable equals 3.
Would you have? Okay, so then experience 1 to 4 equals 3, so we don't need the original variable. Oh, I get it. Okay, sorry.
Okay. Now we got to do the second one. If experience is less than 4, then experience 4 to 7 is what?
0.
0. If experience is greater than or equal to 4, then the second variable is
Experience minus 1.
would that get me this part?
Greater than or equal to
Experience minus something.
4.
4, yeah. Where it left off at. So this is an example of one predictor in terms of concept, experience, but being represented by two different slopes. Okay, questions? Now, what if I wanted to generalize this and add a third piece? Could I? Sure, right? Let's make experience grow bigger. That one's still hanging out at 3. Let's say that I want to do another shift to happen at 9. Actually, no, let's do that. We'll make it 7. 7 to 10. Make it, this we're gonna make it there. Okay. So this one's done. 4 to 7 is done. How do I make it done? What value do I assign to it?
The same.
The same, yeah, it's done. Now my new one. It's gonna pick up at 7, 0, and 3. What does it get before it starts? 0. Shut off. Yes, you can. I'd like you to try. I'd like someone to try. Let me know if it works. But yeah. So these linear spline models, these require you to decide a priori based on data or theory where the breakpoints are. There is such a thing, by the way, as a latent version of these where the data get to tell you where it wants to break, just as an FYI. That's another class, but just so you know, these are best when you have some sort of theoretical defense as to why you would expect 3 different regions, such as in the education example. Now, the other thing that I asked you to do as part of this was to test whether or not you actually needed 2 different slopes. In other words, if each of these slopes ended up being the same coefficient, what would that mean conceptually? Like, let's say that they both ended up being about 2. So for every unit increase in experience from 1 to 4, y goes up by 2.
You don't need it?
You don't need what?
Piecewise, the second slope.
Well, so if I took this out, then if I only had this one, what it would do is that it would go up and then stop. So it would be like this kind of thing. But you're on the right track. So if I said from 1 to 4, every unit increase in experience results in a 2-point increase in Y, and then from 4 to 7, the same thing happens. You combine them. That's an indication that you don't need the pieces, that the two are basically the same slope. So that's what I'm asking you to determine. So how would I figure out whether or not they're different significantly? Do you have any good thoughts? This is an example of a linear combination. So if I have my model that just has, let me take this out here so we can go back to the original story. If I have my model where this is beta 1 and this is beta 2, and I want to know if this number that beta 1 represents is different than this number that beta 2 represents. What am I asking? Different from.
Just do subtract them?
That's
And
it.
if it doesn't equal 0?
That's it. It's just the difference in the coefficients. And you've already seen an example of this when we did, go back to part 1 here. Right here. How to get the non-reference difference. That's beta 2 minus beta 1. Exact same thing, just a different way of interpreting it. Now you could do this for any predictor. If you wanted to know if the slope for x1 is significantly greater than the slope for x2, you could ask the difference as a linear combination. They have to be on the same scale for it to make sense, but you can do that for any kind of slope. Okay. So, how are we doing? Feel better yet? Feel more doable?
This one's hard, like that.
It is. This is normally like a 3rd or 4th stats class concept, but I decided to spring it on you because I think you can handle it. I know, right? But just think how easy it'll be when you get there. So, any of that you want to hear again? So the idea is that we only want to have the slope active, so to speak, capturing changes in x during certain regions of x. So while it's active, the variable increases as x increases, or decreases as x decreases. While it is inactive, it needs to stay wherever it left off, or it hasn't started yet. So this is a different concept than the dummy coding, which is for groups. Because in that case, we're not trying to create a slope. We're creating just a 1 difference. So do you want to do dummy coding? Why not, right? It's your reward for trudging to school on a snowy day. So we've got, in the mini golf example, we'll say we got control, mini, reg, and both. Make this centered. And for those of you who have already started this and sent me your code, I was pleased to see all of you use the exact same naming conventions that I did. C versus M,
Yeah.
C versus R. Yeah, you get very tired of typing real quick, so you come up with the shortest possible names. C versus B as the 3 variables. So I told you that control is your reference, right? And because I have 4 groups, you know that I need 3 slopes, right? So what goes here, because control is my reference? 0, correct. All right. Now, if I want this first contrast to represent the difference between these two, specifically, what goes here? 1. That means what goes here? And 0, right? Well, if this contrast is already locked down as control versus mini, then I'm going to 0 these guys out. What goes here if this contrast is supposed to be control versus regular? 1. What goes here? 0. And then last but not least, what goes here? 0. What goes here? 1. All right. So which of these groups is going to have the mean given to you directly as a model parameter? Only control. The others are linear combinations. So if this variable right here is beta 1, this variable is going to get beta 2. Come on. There we go. Yeah, it's like I'm not playing. And I'll just throw beta 0 up here, right? So if we want the mean for control, the model is beta 0, right? The end. If we want the mean for mini, it always starts with beta 0 plus beta 1. We pick up this one. Mean for reg starts off with beta 0 always plus beta 2. Mean for both starts off with beta 0 always plus beta 3. Okay. How many differences are there amongst 4 groups? 6. How many are given to you already directly as model parameters?
4. Sorry.
How many differences? 3. They're right here. All of the differences of control versus each of the others, those are your betas. That's what's going to show up by default on your model. Now we got to get the other ones. Well, you already know what the mean is for each group. So we just have to figure out literally what the difference is. So if I wanted to do, for instance, mini versus both is one that I asked for, because that would give you sort of the unique effect of regular golf training. If I took beta 0 plus beta 3 minus beta 0 plus beta 1. So that's how I get the mean difference. You have to look at what the model says the mean is for each, and this literally subtract.
So this is like if we're trying to find MVB.
Yeah.
Okay.
Yeah, it's implied by the model. You don't have to code for it. So what's the difference between these two things? Well, if we go beta 0 plus beta 3 minus, order of operations matters here, what do we end up with? Beta 3 minus beta 1. What if I wanted to do the same thing? Yeah, go ahead. So the mean for both is this part. If I want the difference of the mean for both and the mean for mini, that's subtraction. The mean for mini is this thing in parentheses.
Oh, I did. Please excuse my dear Aunt Sally, so I got it the wrong one. Okay.
What does that mean?
You know, like when you like algebra, or so I was like, okay, so -1 times BO, so that cancels out BOs.
Yep.
And then so I had B3 plus B3 minus B. Oh, wait. Oh, okay, sorry.
Yeah, the BOs drop.
Kelly's math issues up here are coming back.
Oh, mine
That's
too.
always been.
Please, parentheses.
That's like
Oh, this
order
is
of
coming
operations,
back,
right?
yeah. Sorry, that one's gone. I got SOHCAHTOA. Does that mean anything to you?
Yeah, sine, cosine. I can only do mnemonics.
Yeah, there are just the words floating up in here. But yeah, these are linear combinations. What if we wanted to do both versus reg? B3 minus B2. So this coding scheme, known as dummy coding, sometimes known as contrast coding, but not always. That's usually reversed to something different. It's sort of the most straightforward way to do it. But there's other things that you can do that might be more appropriate in terms of what you want the model to give you directly and what you want to find as a linear combination. So let me do another one here. So this one has actually come up a couple times when I've given people advice. Let's say that you are looking at group differences, and you have one type of majority group and two types of minority groups. So I could do the same thing where I make one group that's the difference between majority and minority 1, and another one that's majority versus minority 2, and then I could get minority versus minority. But what if my research question is, what is the effect of being a minority, period? And then, does it matter which version I am? Well, I could set up my codes to do that. So major versus minor. And then I would do minor 1 versus minor 2. So this is a different coding scheme that would give us this information directly. So if I want majority as my reference, what goes here? 0, 0. Okay. Sorry, I have to have these aligned. I'm just really anal that way. Okay. Now, this one, if I want to contrast these two together, same value. That functionally averages them. Now here, I'm going to shake it up a bit. Minus 0.5 and 0.5. Yeah.
They have a way between the minor 1 and minor 2. Why don't we just separate them to half?
So I'm basically lumping them together on purpose. And then the second variable, what it's going to do is differentiate them.
But why can't you do the negative 0.3 and 0.7?
You mean to keep track of the size of the groups? Yeah, you could do that too. It's a question of what your inference is. If you want to keep track of the exact size of the groups, then that will give you a different answer than if you want to just weight them equally. A lot of what happens in these group-based designs is that they do end up with equal weighting unless you choose not to. That's another choice you could make. Yeah. Yeah, but this assumes equal sizes. So what happens when they both go in the model is that this first variable gives you the difference between majority and the average of the minorities. This second variable straddles 0 so that the intercept still refers to just a majority case and gives you a unit difference between the two. So then this second coefficient tracks minority 1 versus minority 2. So the rules are still the same. If I have 3 groups, I need 2 slopes. It's up to me how I set them up, what I want to know. The other example that I have that we haven't talked about yet is another type of, it's piecewise coding, but it ends up looking a lot like this group coding. So let me show you that one. It's the idea of testing whether or not an ordinal variable should be treated as interval. So we haven't talked about this one yet. But I wanted to show it to you. It's not in your homework, but just as a concept that you can take with you. So this is slide 39. So there is a variable in the GSS data set that ranges, asks you on a 7-point scale how happy you are. Almost nobody said that they were less than unhappy. So life is good for these people according to their self-report data. So unhappy, neither, fairly happy, very happy, and completely happy. There are a number of people in the world who would see no problem with estimating a linear slope and talking about a 1-unit increase in happy. Yes, that face. Like this is an instance in which there is an ordering clearly, but the numbers are arbitrary. So putting a linear slope through something where the numbers are all squishy should make you make that face. That makes me squishy too. So here's what the relationship between income and each level of happiness actually is with the solid lines. And this is what it looks like if you try to put a linear slope through it. The slope is not significant. So happiness does not, more money does not get you happiness, I guess would be sort of the thing here. But we can test for this type of variable whether or not one slope is sufficient or whether we need one for each junction. Just like the piecewise slope that we talked about earlier. So the dummy coding scheme, where I would say one of my groups is the reference, for instance, unhappy, and then I look at the difference between each of the other groups, that would not directly tell me about the slope between each point. It would give me a difference of the reference group with each other, which is less useful. So what I ended up doing is a different type of coding scheme. So it's easiest to understand what's happening, I think, when you look at the SAS code and look at what happens with the coefficients. So happy 5 is the original variable, 5 category happy. It starts at 3 as the lowest one. I have deemed that my intercept. So all of my contrasts zero out. If I go from happy equals 3 to happy equals 4, the first variable picks up that shift. If I go from 4 to 5, the second variable picks up that shift, but it's cumulative. So each new variable it picks up the next one. So you can see the ones go like that. So it gets me from 4 to 5, and then 5 to 6, and then 6 to 7. So it's like a little moving window, rather than unhappy versus each of the others, which is what it would be if we used this type of coding scheme that we did for golf.
Logistical question.
Yeah.
When we're doing this in SAS, we run this, we type this up, run it, then go to the model? Or do you suggest that we type it all out and then run it all together? Or does it matter?
Well, it matters so that the variables that are in your model have to be created.
So we have to do that first.
You have to do this first.
This is creating a variable.
Yes, it is.
Okay, I get mixed up on this part too. Okay.
Yeah, so this is within a data step, and then these variables then show up as predictors in your model. So they have to exist in order to become predictors. And so then the successive differences in these differences I have asked for. Is the slope going from 3 to 4, which is this one, different than the slope going from 4 to 5? That's that contrast. Is the one going from 4 to 5 different than 5 to 6? That's that contrast. And then 5 to 6 to 6 to 7 is the last one. So I'm taking it in pieces and trying to see if each of the changes suggests that you can just draw one line through the whole shebang or not. The Stata code is on the next slide. I did it a little bit shorter because I don't know how to do the if then do end combination there. And then this is what ended up happening. So overall, the model, meaning the set of 4 slopes here, is still not significant. If we look within each of these, beta 0 is the expected income for somebody who is unhappy. $15,000. Beta 1 is the first piece here. The difference between unhappy and neither is 1.6, which is not significant. Beta 2 picks up where that left off and carries the next one. A slight decrease, not significant. Beta 3, an increase from fairly happy to very happy in predicted income. And then from very happy to completely happy, it goes down non-significantly. And then I have the differences of these slopes in between. None of them are different. So the conclusion that I would draw, with the exception of this one thing here, which is just barely significant, yeah, money and happiness don't seem to be related. You could draw one slope through it because that slope doesn't matter. But you could draw 4 slopes and only one difference matters. So that's another type of coding scheme to give you sort of a moving window. And so then the rest of the stuff here, yeah. I think everything is pretty much the same as what you just saw. Yeah, there's happy 3, there's the pictures. Ta-da. And as always, words. So, in contrast to the homework, my handouts will live on my website forever. So I may take, I will make a new one each time I teach in the new class, and the old one will probably be hidden, but I will always have it, so you can always get it back. But I would save these files as well, just in case I'm teaching it and we haven't gotten that far yet. And you don't have to bother me, but I plan on keeping my website forever. So. Okay. So other questions about coding, pieces, stuff like that?
I'm running into problems where, so if you look at slide 40, where it says output out, every time it's showing up red.
Oh, this?
Yes, so is this something, am I supposed to change?
You don't have to do that at all. You can just delete it. What this is doing is taking, it's creating a data set of, taking your current data set, making a copy, calling it this, and adding 2 columns, the predicted happiness for each, or excuse me, the predicted income given a person's happy rating and the standard error of that prediction. So I did that just so that I could make pictures.
Okay.
So you don't have to make pictures. So you can get rid of that. This wouldn't be necessary in any of the things that you need to do. The estimates are the only thing that it would be necessary. Yep. All right, other questions? You look unhappy, Gabby. No, you're happy? Just excited to go get some candy? You already had some? Atta girl. Yes. So yeah, this stuff is non-trivial. I'll give you that. But there's a logic to it, and once you sort of crack the logic, then you can't unsee it. It just takes a lot of practice to get to that point where it's somewhat automatic. And the pieces is challenging in particular. But do you want to talk about some new stuff? Yeah, why not? We got some new stuff. So lecture 6, I'd let you know, is available. Starts off with a little bit of review, so that'll be good. Now we're heading to the situation where we have more than one predictor variable in the same model. And the big picture, they have to compete against each other. That's what's going to happen. To see who has unique information to provide. So the example that goes with this is almost done. Hope to have that up sometime tomorrow for next week. So we'll do lecture 6 here. So first off, reviewing. So what happens in linear models in general? The role of each predictor, which we call X's, in creating a custom expected outcome for each person is described through one or more fixed slopes. So if you only have a binary predictor, you only need one slope to indicate the difference between one group and the other. If you have a quantitative predictor and you're happy with giving it a linear effect, then you only need one slope for that. You need more than one slope for nonlinear effects of quantitative predictors that reflect quadratic or piecewise trends. And for categorical predictors, you need C-1 slopes. So if you have C groups, you have -1 because the intercept is one of your groups, and each of the slopes then differentiates the intercept from each of the others. And in each of these cases, we end up with an unstandardized solution. So what that word means, unstandardized, is in the metric of the original variables. So you have to know what a unit is. Is it a pound? Is it a year? Is it, whatever, what have you. So we end up with an estimate for each slope, its standard error, which is a function of the residual variance in the model, as well as the variance in the predictor and sample size. Estimate divided by standard error gives us t, and then given numerator degrees of freedom 1, because we're testing one thing, and denominator degrees of freedom of what's left over, sample size minus the number of fixed effects, we can then get a p-value that goes with t, and this thing right here shows up automatically on your output, and we call it a univariate wall test. Some people would get angry at the term wall test for a t, but I'm not one of them. If anybody gives you, hassles you about that, you can say it's a modified wall test because it's using t, not z, but that's what everyone's going to use. If you want to have an index of effect size, we can convert t into r or d, or ask for standardized slopes. So what are effect sizes useful for? Lots of things. Can you give me one? Why would we need to go to the extra trouble to ask for an effect size for our slopes?
Magnitude of the change?
Magnitude of the change? Yeah, so like if I told you my slope is 12, you'd be like, okay, is that good? I'd say, well, it's significant. Okay, that it just means you have enough people. But how much is 12, right? Yeah. So effect size is used to put it into a metric that people readily understand. D is standardized mean differences. R ranges from -1 to +1. So standardized effect sizes help convey the absolute size of an effect. They are used in study planning to assess power. There's a number of journals now that want you to do a power analysis to go with your study to say how much power that you had, like post hoc. And also meta-analysis. Have you heard that term before? Meta-analysis is when you're pooling the results of studies. What you end up pooling are effect sizes, because each study may use a different version of the predictor or dependent variable. The effect sizes are on the same metric in theory. So it's helpful to people who want to try and pool your results or generalize them to give them standardized effect size in addition to the unstandardized scale-specific solutions. So reviewing what fixed effects mean when you have only one predictor. So if I have just beta 1, the intercept is the expected outcome when this x1 is 0. The slope, difference in y per unit change in x1. And the standardized slope would be the same thing as the Pearson's correlation, bivariate correlation. So the unstandardized slope is like Pearson's R in the metric of the original variables. E is the difference between what the model says and what you have. Same thing would be true if we have x2 by itself. The intercept is conditional on a different predictor being 0. The slope reflects the effect of that predictor, and E is defined the same. So this is all good, right? Okay. In terms of the model, if you have more than one fixed slope in your model, then you want to know whether or not your model works to explain variance as a whole. That's where we are asking whether or not the proportion of variance that's explained, R square, is greater than 0. That is known as a multivariate wall test. The idea that you're testing more than one term simultaneously to see whether or not that gives you an R square worth talking about. So the test for that is F, which I've given you the variations of F, but the big picture, it's information that is known relative to information that is unknown. And you can see that most clearly if you look at the last version. R square is on the top, 1 minus R square, meaning everything that's left is on the bottom. So F is evaluating how good your model is per degree of freedom spent to make it that good. And if we have only one fixed slope, the t that we get for that fixed slope is the same if you square it as the f for the model. So model f is only relevant when you have more than one fixed slope. Okay, so moving on. Everything we've done so far in terms of mixed slopes is fixed slopes mixed across one variable is to try and talk about the effect of that one variable. So it may take more than one slope, but it's still one concept. Now we're changing to talk about what happens when we start putting multiple variables into the same model to see the unique contributions of predictors. And so this is a word you're going to start seeing on like every slide, unique. If I have x1 and x2, what does x1 do for my prediction of y that x2 doesn't do, and vice versa? So it's all about trying to figure out the pattern of redundancy versus unique prediction for each variable. And what this means in practice is that the standardized slopes on your output are no longer equivalent to the bivariate Pearson's are, meaning just the correlation between x and y, and instead are related to something called a semi-partial correlation. A synonym for that, by the way, is a part correlation. So here's a real-life example. The show This Is Us. Does anyone else watch the show? Yes?
I did till I got too sad.
It's not sad. Jack can only die once, so.
Keep bringing it up. Yeah.
It's drama. Like, they're not over it yet. So yes, this is one of my favorite shows. This is Us. So for those of you who are not fans, the premise is that it follows one family, but it goes back and forth in time. So this is the cast of them sort of, well, the kids as they are now. This is them from like the 70s, and this is the kids that those people were. So it goes back and forth and shows them, like, I think they're 11 maybe in this picture, give or take. And so it shows their childhood, and then like it was a whole thing because at one point during the first season, it became obvious that Jack had died because he's not in this picture anymore. And so then it's like, okay, what happened? And that was actually after the Super Bowl that year. Like, that's how big the show was. They finally revealed how Jack died. He died rescuing his daughter's dog from their burning house.
A lot of controversy.
I know.
Lots of nurses weighed in said he could have been saved.
Like Jack
Well,
in Titanic.
Yeah, no, he rescued his whole family, and then he heroically went back into the burning building to get the dog. So that was the thing. So anyway, this is my example for unique effects and regression here. House cleaning with the Pearson family. So let's say that Rebecca, she's the perfect looking mom who is like always perfectly made up and healthy and, you know, fit no matter what age she is. She's had it with her 3 messy teenagers, and she provides an incentive for them to clean the house. Let's say the Pearson house before it burned down had 9 rooms that were cleanable. 4 bedrooms, because each kid got their own bedroom once Kevin moved into the basement. 2 bathrooms, we'll say, since that's 5 people, that seems reasonable. 1 living room, 1 kitchen, 1 dining room. So she comes up with an incentive system for the 3 kids and Jack, because he needs to help too. So for every room you clean by yourself, you get a new Nintendo game. And my little brother is the same age as the Pearsons. He was born in 81 with them, so like I know that Nintendo when he was 11 was like the thing, right? They were like $70. It took all year to save up all of his birthday and Christmas money to get 1 Nintendo game. So it was a big deal. But there's also a bonus, she's willing to say. If an average of 2 rooms per person gets cleaned, 8 or more rooms, we get a new TV. That's how much she wants her new house cleaned, her house cleaned. So she decides she's leaving for the day. She's going to go do yoga or shopping or whatever it is that, you know, makes her look so perfect. And she returns home and asks who did what. So let's say here's the situation. I made a chart. If you just look down the list of rooms, somebody tackled everything. All 9 rooms are clean, so the family gets a new TV. Hooray! Now we got to figure out who gets how many Nintendo games. So we start with Jack, Kevin, and Kate, who each managed to clean their own bedroom. So no one else cleaned their own bedroom, so they each get 1 game.
Randall did.
But now he's next. Now Randall cleaned 3 rooms that no one else did. He gets 3 games because Randall is a perfectionist overachiever, and that's just how he rolls. Yeah. Now what about the bottom here? the kids, each of them claims to have cleaned the living room, but Rebecca wasn't there. She doesn't know what really happened. It's just as easy to take credit for what work someone else did. Likewise, Jack says he did the kitchen and dining, but Randall didn't think he did a good enough job, I'm guessing, and so he went back and did it too. So we can't give anybody credit for the common rooms, to be fair. But we do give the family credit for having cleaned all 9. So general linear models, regression as we're doing now, is all about this process of figuring out who gets credit for what. And what's going to end up happening is that each predictor gets credit for the part of the prediction that it can be demonstrably theirs. But anything that's in common, the predictor doesn't get credit for, but R square still takes it into account. The whole or the part. So yes, from cleaning to modeling. What we're looking for is 2 things. In general, do the predictors work together to explain a significant amount of variance in an outcome? Is the model R square, the square of the correlation between the predicted Y and the real one, significant, significantly greater than 0, which is an F test for that. And R square is a function of the common parts of the prediction as well as the unique parts. Specific utility then is what does each variable contribute that the others don't. And so this thing, this picture is known as either a Valentine or a Venn diagram. You may have seen these before. So we have Y as the outcome that's being predicted. I've got 2 predictors here, x1 and x2. So the part of x2 that uniquely relates to Y is A. Because if you follow the circle here, A and C characterize x1, but because x2 also has C, x1 can only get credit for A. Likewise, x2 can only get credit for B. But A, B, and C all work together to account for variance, and what's left over is E. So each of these areas is referred to as a proportion of variance. Then we get some math that goes along with this idea. So how do we figure out what the slopes and intercept would be from a model that has both x1 and x2 at the same time? So I gave you a comparison of what it looks like from one predictor up here. The intercept, its job is to capture a difference in the means of each variable, so it adjusts for scale. The same thing is true when you have 2 predictors in the model. It has to adjust for the means of both, so it's still just doing that. Beta 1 used to be just the correlation between the variables rescaled as a function of their standard deviations. Here's another version of the same formula that you will see for beta 1. Now the new beta 1, if I write it in terms of correlation, forget the scaling for right now, just the correlation part. This notation right here, this y comma x1, this is the correlation of y with x1. This one right here, this is the correlation of y with x2. And the third one is the correlation of x1 and x2. So roughly what these formulas are showing is that the standardized effect of beta 1 starts with whatever its full relationship is and subtracts the part off that's redundant. That's the big picture. And the same thing happens in trying to figure out what beta 2 should be as well. So an effect size that goes with this concept then, just as we had Pearson's correlation for a bivariate relationship, like the full size of the relationship between x1 and y is given by its Pearson correlation. The full bivariate relationship, or zero order as it's called, between x2 and y is given by its bivariate correlation. We have a new word, semi-partial. I don't know who made this up, but that is what it is called. It is called semi-partial. It's also called part. There is another word called partial that is not that. That's a whole separate thing. Just pretend that doesn't exist. It's related, but it's not going to be of use to us. So yes, semi-partial is the relationship between y and the unique part of x that is unrelated to the other predictors. That's what semi-partial correlation means. And so if I take the semi-partial correlation for x1 here and square it, that's what A is supposed to convey, a proportion of variance. So proportions of variance are in squared metrics, correlations are in unsquared or square root metrics. So area B squared is the semi-partial squared, for x2 is area B, and C is the common part that no one gets credit for, but it still goes into R squared as a function of that. So here's some more math to show you that I'm losing it. Semi-partial correlations and standardized slopes are related. The end. That's what this says. They're not the same, but they're close. They differ by their denominator. One has an extra standard deviation of x in it that the other one does not. So that is to say, when you want to report effect sizes for these new unique effects, you have to be clear which one you're talking about. So if we put them together and we want to interpret the fixed effects, start with this one here, intercept. It's the intercept is always the expected outcome when x is 0, but now it's when all the x's are 0. So x needs to have a meaningful 0 for this reason. Slope of x1, it's the unique difference in y for a 1 unit difference in x. And so I've given you 3 different ways that you may hear people talk about this. The idea of unique is conveyed by saying controlling for, or partialing out, or holding constant. The one that I probably say most frequently is controlling for. Holding constant is one that I also hear people say. Partialing out, less so, because that partial word gets confusing. But the idea is that you're trying to say, what does x1 bring to the table in predicting y that x2 doesn't? And the number that you end up with for its slope conveys that in an unstandardized scale-specific metric. So whenever x1 and x2 are correlated, the slopes that you get here will be different than what they would be if either predictor were by itself. Not necessarily smaller, although that's usually what happens, but different. Because the correlation between the two makes them sort of fight it out for who's getting credit for what each one can bring. The slope of x2, same way. It's the unique effect on y of x2 after controlling for x1. So these unstandardized fixed effects can be useful for creating predicted values in the scale of the original outcome. But because each of them depends on what a unit of x1 and x2 is, you can't compare them. So like if x1 has a slope of 12 and x2 has a slope of 1, I can't say, well, 12 is bigger than 1, so x1 is more important. It depends on is it years, pounds, inches, what is it? So you can't look at those numbers and come to any sort of meaningful conclusion if they're on different scales. One other thing that happens in terms of reflecting the idea of unique is that the standard error for each of these predictors has a new component to it. So previously, the top formula here gives you your standard error for a predictor that has only one slope in the model. It's a function of, just like the standard error of the mean was, variance on the top and sample size on the bottom, corrected for the number of fixed effects, and also correcting for the variance in x to change the scale. All of that still applies, but now there's a new term shoved in here. It's trying to take the variance of x and correct it for how much the unique variance is. That's not predicted by the other predictors. So what does x bring to the table that the other ones don't? The standard error is trying to capture that. So the standard error is going to be smaller to the extent that either the models works better, so there's less residual variance left, or x has less in common with its predictors. the more X has in common with the other predictors, the less unique variance it has, the higher its standard error is. So it's harder to figure out what someone uniquely brings to the table, the more like the other predictors they are. That's what it means. There's less information there to work with. All right. How are we doing? Yeah? So same concepts, just this unique thing. So what it actually means to say controlling for or partialing out. You can think of this literally like for everybody who has the same value of x2, like x1's slope would tell you what the effect of x1 is. That's what holding constant is. You can also think of it in terms of residual variance for the predictors. So if you took x1 and predicted it from x2, you save the residuals, the part of x1 that's unrelated to x2, and you stuck that in the middle, in the model, excuse me, I'm really losing my words here. Stuck that in the model instead of x1, that's what the slope would still give you. So it literally is the part of x1 that's left over after being predicted by x2, that's the new predictor in the model. It does it for you so that you don't have to do that. You could do that as a conceptual exercise, but I don't want to confuse you anymore. So holding constant just refers to the idea of the unique part, and the model figures that out for you, how much is unique and how much is common. And you should all watch This Is Us because it's a great show.
I'm inspired to go back and.
Hulu, it's on Hulu.
But now we know how we did.
Yeah, I know, but like you were gonna find that out in season 1. Plus, Kevin's really hot, so there's that.
It was disappointing, so it's better.
Yeah, but well, and now they've introduced a whole new generation this season, so there's all new people to keep track of. That it's getting complicated. So yeah, that's what I would say. But do I at least get credit for trying to give you a real world example?
It's
That was
good.
great.
Thank
It
you.
really
But I was
helps.
just thinking about, they did not think that through. They should have done some planning, or they maximized the number of video games that we've got.
Yep, they did
Right.
not.
Oh,
No,
yeah.
they're too busy fighting amongst themselves, right?
I
As
was like,
children.
oh, we missed out on some video games.
I know. Well, Randall would have cleaned the whole house if he could have, right? He just probably ran out of energy at this point. But yeah, I was making these slides, and I'm at home, and my husband walks up to me. He's like, "What are you doing?" I'm like I'm teaching. But yes, watch the show. Maybe I'll pull in Grey's Anatomy next time because that's my other favorite show. So, Kurt.
That's how I learn English.
So you become fluent in things like seriously.
Yeah.
That was their catchphrase. So anywho,
I had my heart break when McDreamy died.
oh, I know that was the worst.
Right.
Yeah, I knew it was coming, but it still didn't make it any easier. I know. And McDreamy, also quite attractive to look at. Yeah, well, that shows Dr. Cass. Like, they always have perfect hair, perfect makeup. And, apparently after a 10-hour surgery, the first thing they want to do is go have sex with their coworkers in the on-call room. As after pulling a 10-hour shift, I'm sure that's what all the rest of us would want to do too, But I digress. All right, happy Halloween, friends. Go out and have some fun. Stay safe, and we'll see you next week.